Apple's new iPhone 17 Pro Max just dropped and longtime users are asking the same question. Is this really new? The same 8 times optical quality zoom, the same 8 gigabytes of RAM, while Android flagships have moved far beyond, and still the same $1,199 starting price for features many users expected years ago. It's a familiar story. Polished ads, refined materials, and minor tweaks that keep Apple's profits soaring, but not the technology itself. But this next year, something different happens. Tesla stepped into the ring. The newly leaked Tesla Pi phone is a category reset with hardware that dwarfs Apple's specs and real free distribution deals for early adopters. It's rewriting what value in 2025 actually means. All of these new updates will be included after 10 seconds. So hit that subscribe button if you're ready for a breakdown that exposes what Apple doesn't want you to know. 1. How does Tesla's camera system deliver 15 times optical zoom when Apple can't break past 8 times? The camera specification difference between the PY iPhone and iPhone 17 Pro Max isn't about megapixel counts or computational photography buzzwords. It's about fundamental optical engineering that Apple has either been unable or unwilling to implement. The iPhone 17 Pro Max uses a periscope telephoto system that achieves 8 times optical zoom through a folded lens pathway, which is the same technology Apple introduced 2 generations ago. It's competent technology, certainly better than digital zoom, but it's reached its architectural limit within Apple's design constraints. The PY phone, by contrast, implements a quad-prism periscope array that achieves 15 times optical zoom through a completely different optical pathway architecture that requires precise manufacturing tolerances. Apple's supply chain hasn't mastered at scale. The technical foundation for this advantage comes from Tesla's partnership with advanced optics manufacturers who've been supplying camera systems for SpaceX equipment. Where optical precision isn't a luxury feature, it's mission-critical infrastructure. The quad-prism design allows for multiple light path folding stages within the same physical depth envelope, effectively tripling the optical pathway length compared to Apple's single-prism periscope design. This isn't theoretical physics. It's production-ready technology that's already been validated in ruggedized equipment operating in environments far more demanding than a smartphone pocket. The lens elements themselves use crystalline calcium fluoride components that eliminate the chromatic aberration issues that plague extended zoom ranges in conventional glass lens systems, delivering sharpness across the entire 15x zoom range that actually rivals dedicated camera telephoto lenses in the 400mm equivalent range. Beyond the telephoto capabilities, the PYO's wide and ultra-wide sensors implement something Apple has been promising but never delivered: true variable aperture mechanics across all lenses. The main wide sensor operates with a mechanical aperture that adjusts from aperture ratio of f to 1.2 to an aperture ratio of f to 5.66, allowing genuine depth of field control that mimics professional camera systems. This mechanical aperture adjustability also means that the lens can open wider to let in more light or close down to limit exposure. This is actual optical physics where the lens physically controls light passage to create depth of field characteristics that can't be replicated through software algorithms. In practical terms, this means the PY phone can shoot in extreme low light conditions in bright conditions to eliminate the lens softness that Apple's fixed aperture design can avoid when shooting in harsh daylight. The ultra-wide lens implements the same variable aperture system, eliminating the exposure compromises that make iPhone ultra-wide shots either blown out in bright conditions or noisy in low light. The sensor technology itself represents another category where Tesla has leapfrogged Apple's specifications. The PY phone uses stacked CMOS sensors with integrated DRAM layers that eliminate the readout speed bottlenecks that cause rolling shutter artifacts in iPhone video, particularly when shooting fast-moving subjects or panning quickly. The sensor readout speed is 6.44 times faster than the iPhone 17 Pro Max's sensor, which translates to video footage that actually looks like it was captured with a global shutter cinema camera, rather than a smartphone with the jello effect distortion that plagues iPhone footage when you're trying to capture athletic events or any scenario with rapid motion. For users in California filming outdoor sports or New York residents trying to capture street photography with moving vehicles, this is the difference between footage that looks professional and footage that screams shot on a phone. Regardless of the resolution specs, low-light performance is where the sensor size advantage becomes mathematically undeniable. The PY-Lens main wide sensor is 1/0.98 in format compared to the iPhone's 1/1.14 in sensor, which sounds like a small difference until you calculate the actual light gathering surface area. But it means that iPhone 17 Pro Max's imaging surface measures roughly 13 millimeters wide, 10 millimeters tall, and 22 millimeters across the diagonal. This is one of the largest sensors ever used in a smartphone. In contrast, the iPhone sensor captures 28% more photons per exposure, which translates directly to cleaner images in low light with less noise reduction processing required. When you're shooting in dimly lit restaurants, evening outdoor scenes, or anywhere that isn't flooded with direct sunlight, that extra 28% light capture means the difference between images that require heavy-handed computational noise reduction that destroys fine detail and images that retain natural texture and color accuracy, even at ISO 6400 and above. Apple's computational photography has gotten very good at making noisy low-light images look acceptable on a phone screen. But when you examine those images on a desktop monitor, the noise reduction smearing becomes immediately obvious. The PY-Phone's larger sensor simply captures cleaner raw data before any computational processing happens, giving it an insurmountable advantage in image quality that software can't overcome. The front-facing camera represents the most dramatic specification gap. While Apple's 18-megapixel autofocus true-to-depth camera is excellent for FaceTime and selfies, the P-Honey implements a 48-megapixel autofocus front camera with optical image stabilization. This is about video conferencing quality that actually matters for professionals working everywhere else, where remote work has become standard practice. The autofocus system means your face stays sharp, whether you're